Alright, so today we're going to review your Gyro's built-in hardware digital low-pass filter, and we're also going to review all the different filter recommendations that are out there and the associated attenuation and latency. So buckle up. Okay, so on this graph I have some of the different gyros that are on the market. You probably have heard of the MPU 6000. That's a classic, tried and true gyro. It's been out in the market for a long time. There's also the 6050. These are both limited to, they can't sample higher than 8 kilohertz, and honestly that's what they sample at, 8 kilohertz or 1. It's either 1 kilohertz or 8 that the hardware actually samples at, and we'll show that in a second. Then there's also a new generation of gyros. New is as in probably the last year, I guess, that can sample both at 8K or 32K mode. What some may or may not know is that at 8K mode for either set, your digital low-pass filter is around 250 to 256 hertz. In 32K mode, the digital low-pass filter is set to around 3000 hertz. So that makes a difference in your noise attenuation. In addition, the new filters pick up, since they're a lot more sensitive, they pick up a lot more vibrations because they're sampling a lot more. So let's pop over into Betaflight and take a look at the settings for the digital low-pass filter. So if you go to the CLI command and you type get gyro _LPF or just get gyro, this will come up as one of the options. You can see you have a bunch of options here for setting your digital low-pass filter. And it's set to off, but off doesn't really mean off. We'll talk about that in a second. And then there's other cutoff points for the digital low-pass filter. You can see here 188, 98, so on and so forth, and experimental. Going into the data sheets, we're going to look at the MPU 6000 first. So when you set your digital low-pass filter for obviously 188, 98, 42, these are the cutoff frequencies. What's really interesting about that is if you ever would set your gyro to 188, 92 to help with noise, no matter what you have your gyro sampling rate set to, it's now going to start to sample at 1 kilohertz. I don't care what it says in Betaflight in the configuration tab. The gyro is going to override that and sample at 1 kilohertz. It's very interesting, if you're running iNav, I believe its default is 188. So if you are running iNav on a GPS build, go ahead and take a look at that. For the digital low-pass filter setting of off, which is very misleading, it's not actually off. It sets a cutoff frequency at 256 hertz. And you can see it has an associated delay of 0.98 milliseconds, or essentially 1 millisecond. And then it's doing its sampling at 8 kilohertz. Note that the reserve down here for number 7, that's associated with experimental. And right now, as of the last, I don't know, week or so, there's some people that are starting to experiment with that. But we're really not sure what low-pass filter that provides. It looks like it definitely raises it, causes a bunch more noise. Unless you're into experimenting, you never want to set your gyro digital low-pass filter to experimental. Never ever. You could smoke a motor almost immediately. Off is the default. You're going to leave it at off. Going into some of the other gyro settings, you can see in here, so now this is the MPU 6500. That has the same. The cutoff now is 250 instead of 256. A little less latency. Essentially the same settings. And you can see experimental on this one, because it's associated with the same digital low-pass filter config number 7, sets its cutoff at 3600. But look at how much lower the latency is, 8 kilohertz. Now in 32 kilohertz mode, you're going to get 32 kilohertz sampling rate, and the default is 3600 for your cutoff. I don't believe there's a setting in the code yet for Betaflight to actually set to change your cutoff up even higher. Like experimental, I don't believe sets it to 8800 for a cutoff in 32K mode just yet. I think there's a hack in there for certain gyros, but I haven't really looked into it. Again, I would recommend staying away from that. Many of the others, the 9250, it's just more of the same. So I'm not going to pour over this, but I'll just bring these up so you can see them. And then down here, this is the IMC series. Again, more of the same. Some of the cutoffs are a little different, but the sampling rates are the same. These don't have published latencies, but I'm assuming they're similar to the others. Now this ties into our handy-dandy filter latency calc sheet here. You can see on the right-hand side, or the left-hand side, that you can pick your different gyro types. And I only have a couple here, the 6000, the 6500, and the IMC series. And then you can pick your different cutoffs. So if you pick in 32K mode, you can see it goes up to the 3000 kilohertz cutoff. And then obviously you'd have to pick your PID loop rate. So you do have to be cognizant of what you're setting, hence this video, and know what your gyro is doing and what the appropriate settings here. So if I'm running an MPU 6000, I know that I need to know that I can't go above 8 kilohertz, and then obviously off would be the default. That gives me the 256 hertz cutoff. Some people have asked, notice there's a linear latency or linear delay. You can see in the published documentation they only provide one number for delay. We do not have, as far as I'm aware, and if anybody knows, there's not really good documentation out there. There's good reason to believe it's very similar to a FIR filter, where the delay is constant across all the spectrum band, and that's what this is modeled as. If anybody has any documentation otherwise, please let me know. The specific settings are over here on the right hand side. Essentially, when you're picking those drop downs, it's just picking from these tables here. So I wanted to go into a little bit of where does all this 32K sampling and this stage 2 filter, how does this all kind of come together? And just some basics on filtering. So a couple terms you're going to hear are octave and decade. I think decade's pretty simple because when you're looking at a logarithmic graph, that's what you'll see a lot of. If you see any of these noise attenuation graphs, they're all log graphs. A decade is a multiple of 10 years in a decade. Pretty simple to remember. An octave is the current frequency times 2. So how I kind of remember it is like keys on a piano. This C key here, and then if you go to the next C key up here, this is twice the frequency of the lower note. So just that, you can kind of hear that through experience of, okay, I recognize on a keyboard if I hit this key and then I go up, it's like twice the pitch. That's what an octave is. Now when we come down, you'll see noise attenuation graphs. So it's like, it's 3 dB down at a certain cutoff and 6 dB, and what the heck does that mean? Well, 3 decibels down essentially means it's going to take whatever the amplitude of the sine wave is and cut it in half. If it's 6 dB down, it's going to cut it in a quarter. 9, it's going to cut it in an eighth, so on and so forth. So cutoff frequencies of all these low-pass filters for the classic stage 1, PT1, you also have the option of biquad, which is twice as steep as the PT1 but has twice the delay as well, and FIR. Those cutoffs for at least the PT1 has a -3 decibel attenuation right at the cutoff. As you go down, this is the slope of this line is 20 dB per decade. So you can see here 20 decibels down. I'm going from 100 to 1,000, and you're 20 decibels down. What we're going to go ahead and do is turn on our notch filter. So coordinating with the developer that introduced the notch filter, the dynamic notch is generally running -30 to -40 dB, which is huge if you look at how much attenuation that is. And I'll pop over to a graph in a second on that. So you can see it really cuts wherever that notch filter is. It's really going to cut out the motor noise. If 3 dB is half of it, 9 is a quarter, and then we're going all the way up to 30, 40. We're cutting 0.001 times whatever the amplitude is. That's how much we're cutting out. So as we go into 32K mode or experimental mode, if you wanted to be very cautious and look at that for the MPU 6000 gyro, it's moving that digital low pass filter way up from 250 to 256 hertz, around there, and it's moving it all the way up to around 3000 hertz. However, the issue is there's not enough filtering. There's this gap. This line keeps attenuating noise. So now we're down to negative 20, negative 30, negative 40 as it goes out. So this would be negative 40 decibels at 10,000 hertz. So this line keeps going and attenuating down further. But apparently it's not enough attenuation just having one low pass filter. So that's where the stage 2 biquad RC F2 filter or the FKF fast Kalman filter comes into play. And in my previous videos, which I'll link to in the upper right hand corner, I recommended keeping the dynamic notch on and setting that around 500, because you can see that's right where the dynamic notch is generally going to be ending. And then your BQRCF2 or fast Kalman is going to attenuate noise from here, from in this range between 500 and 3000, and then it's going to keep attenuating, so you're kind of stacking things up. See, we have cascading filters from the stage 1 to stage 2, and then the gyro's digital low pass filter. The recommendation by the Debs is to just turn off the dynamic notch and slide this back to 500 or 250 hertz, which Joshua Bardwell says he had some really good experience with that. You can see that if we're moving this back to 250, we're going to get 3 decibel attenuation. And around 250 for the stage 1, we're going to have around, let's just say 10 decibel attenuation right here at 250 hertz. So now you're up to 3 plus 10 is 13. So you have 13 decibel attenuation for your peak motor noise, which, that's something. But it's no 30 to 40 decibel attenuation. So I really think it comes into how noisy are your motors? How big is that spike for your motor peak motor noise? If you look at gyro traces or looked at black box logs a lot, you know that it does not take very much noise at all to get through to the D term, for the D term to be overactive and have way too much noise on it to turn off, or to turn the low pass filter in the D term from biquad to PT1, and then ultimately turn off the notch filter as well. So we really got to attack that motor noise. To me, that's what notch filters do. They really attack high peak noise. Low pass filters are for more flatlined noise that extends out across a long band. So that's what these low pass filters are doing. But so it just takes experimentation. It just takes flying it, see what flies better. And then also I really to me it's not just flying it and giving observations. It's all about looking at the black box logs. The proof's in the pudding in there. Okay, so the 2 filter recommendations or approaches that were outlined initially by Joshua Bardwell I have listed up here on the screen. The first of which, the first approach was by the Betaflight devs, and it really doesn't have the dynamic notch turned on, and obviously the static notches are off as well. Now for this comparison, we're not going to talk about the D term notch and low pass filter. We're not going to look at those comparisons, at least. What we're trying to do is attenuate enough vibration noise on the gyro that you can get to the recommended filter options for the D term, which means a low pass filter for the D term of PT1 and turning off the static notch. If you can't attenuate enough noise on your gyro sampling, you won't be able to do that, and you won't be able to get that optimum performance by doing that. In addition, that both approaches to me have a start and an optimal point, and the optimal point can go even higher than what I have shown here. It really depends honestly, how much vibration? If you can totally get your motors to somehow not cause vibration at all through soft mounting or whatever, some magic, you could really get even much farther with this and much more advanced filtering alternatives that have much lower latency. But let's just stick with a start and then what is reasonable to think that you can get to with enough soft mounting of your motors and or flight controller. So the first approach was, again, the dynamic notch turned off and the stage 2, either the BQRCF2 or fast Kalman filter set at 150 hertz for the cutoff frequency. This is a 32 kilohertz sampling and PID loop frequency. You can see the notches are off, and then the stage 1 filter is on at 90 hertz. So you have two sequential or cascaded low-pass filters that are handling your noise. And it's actually 3 because, just like we talked about, that Gyro digital low-pass filter is up at around 3,000 kilohertz. Or 3 kilohertz, 3,000 hertz. So with that, it starts, the copter motion, this band in red here is from 0 to 20 hertz, and this is from 20 up to 100 hertz. I know I have them backwards, but in my Excel spreadsheet, they're oriented horizontally, so I just kind of rotated them down, and that's why it's like this. But anyways, you can see you're starting at 0.96 milliseconds. Approach 2 starts at a lower latency. You know, with the FKF or BQRCF2 filter at 500 hertz cutoff and having that dynamic notch on, you start at a lower latency. And I argue that you attenuate more motor noise because of what we just talked about, that 30 to 40 decibel attenuation of the peak motor noise. So I think you're starting at a better spot. However, and when we get to the optimal condition, you can see they're kind of the same. 0.02 differential, I think, is outside the spectrum of the accuracy of this worksheet, or realistic conditions anyways. Situations vary. So basically they're the same amount of delay. So then what's the recommendation? Well, there's pros and cons with approach 1 or approach 2. The pro with approach 1 is that it takes a lower CPU utilization, and it shouldn't require you to use overclocking on your gyro because the dynamic filter is turned off, and that takes a lot of CPU utilization, around 10%, maybe less. With approach number 2, so what's the benefit here? Well, you have more peak motor noise attenuation, but that comes at a cost. Has higher CPU utilization. So when people are running this approach, they're getting up around the high 40s. So they're really pushing their CPU utilization. And what you can do is turn your PID loop down to offset that. Again, if you can get away with not needing that higher amount of noise attenuation, well, maybe this is the way to go. Then you have some CPU overhead. But if you can't make this work to turn off your D-term filtering, or turn down your D-term filtering, I should say, then try approach number 2. The other thing that's nice about approach number 2 is that dynamic filter is there as a safety net. So if you ding a prop or have something that goes out of balance, people are using turtle mode a lot. I don't use turtle mode, it scares me. But if you're using turtle mode a lot, so you're flipping over, you don't really know what happens because you can't see the quad, you flip it back over and start to fly it back to you, or just fly again. That dynamic notch may be a good safety feature for you. Make sure you don't smoke a motor. Okay, so let's look at 8K, and the 2 different approaches. So for approach number 1, as far as I'm aware, there's no differential between 32 kilohertz sampling and 8 kilohertz sampling. So you can see it's the same setup, and then you can see the associated latency. Same thing down here. Now, it's different for approach number 2, actually. You have the dynamic notch turned on, but what we're doing is we're not doubling up on low-pass filters anymore. You pick one. And you'd say, well, Mark, if I pick the PT1 stage 1, isn't that the filtering I had in Betaflight 3.2? Yeah, kinda. It's pretty much the same. However, the BQRC and the fast Kalman filter, well, the fast Kalman, that has magical pixie dust in it. So you get the magical pixie dust. and I'm not, it's just poke a little fun. But in the BQRC F2 and the fast Coleman, they actually have a little bit more attenuation, around 500 hertz up than the PT1 filter. So there's a little bit of a, you could argue there's a benefit to kind of swap them out, and then you can see the associated latency with it. So here, your start point, again, a lower latency. Now the optimal point, now there is a spread here. Now we're bumping this up to the stage 2 at 250. Again, dynamic notch off with approach 1. Same pros and cons, but you can see the associated latency down at the raw copter motion is 3.5 estimated milliseconds of delay, whereas approach 2, it's 2.83. So you can kind of go back up. 2.83, we're approaching the 32 kilohertz sampling delay, what you're able to get with 32K. So, by the calcs, when everybody's saying, hey, 32K is better, faster, lower latency, it is. You can see it right there. Just look at the two different options. If you run an 8K, you're going to have a little bit more latency. It looks like Approach 2, to me, gives you the optimal performance. Now, this isn't aggressive. To be able to bring your low-pass filter up to 120 hertz for the cutoff and not have, a stage 1, just using the stage 2 with the dynamic filter. And then, obviously, we're assuming that, in either one of these optimal conditions, you're still able to achieve turning down your D-term filtering. That's pretty aggressive. Not everybody's going to be able to do that. So, the result may be somewhere in between here. I'm not making this up out of anywhere. If you go on to the wiki website, Boris's recommendations, if you have a nice, clean, low noise machine, you should be able to try to get that up to 120. And hey, try higher. If your motors aren't getting hot and your black box traces are looking good, go higher. Go as high as you can go to get that latency down. Now, one thing I wanted to address with the Butterflight recommendation is it seems like there's just one recommendation out there that, on the face of it, everybody's just dumping in. And if you're running 32K, I think you're good to go, because that's very close to my recommendation. Mine was a cutoff, started a cutoff at 500 hertz. Let's go back up. 500 hertz, but then in the optimal condition, I'm taking this up to 711. Well, where did I get 711? Well, 711 is where Butterflight's recommendation starts at. So in a 32K sampling for Butterflight, I think you're going right to the optimal point. Hey, maybe you can move it up higher than that, like I said. However, when you're talking about 8K, what happens with the fast Coleman filter, at least, as you move the gyro sampling rate down, the cutoff frequency for the fast Coleman filter moves down. You can see it at 8K or at 32K. You're running 711 is the cutoff frequency with your QNR of 488. But as your gyro sampling rate goes down, that goes down to 88.9. So it's 89. These are all energy values. So 89. Look at how high that delay is if you don't turn off your stage 1. So here's my argument. At 32K, this is the Butterflight recommendation. You got the stage 1 on, you got the stage 2 on at 711, and then you have that gyro up at 3 kilohertz. However, as you transition and go down to an 8 kilohertz mode, like that animation, watch out, Pixar, I'm coming for you, that you need to turn off your stage 1 filter. That, having both on, having two low pass filters right on top of each other, you're going to get double the latency. It's essentially the same thing as running a biquad filter, which nobody's run that for a long time on the gyro because of how much latency it has. So keep that in mind. The other thing I wanted to mention about this, it seems like with comments, some people are very much into this, like myself, and some people are very frustrated by all the options and the complexity. And these are toys, guys. Just pick what level of detail you want to go down the rabbit hole. Unfortunately, the fact is filter tuning is like PID tuning. If you want to get to the high level of performance, it takes some knowledge, it takes some tweaking to get there. It takes some black box log reviews, things of that nature for filter tuning. If you don't want to do that, and you're saying, this thing seems to just fly fine on the defaults, why is everybody taught? Then just fly it on the defaults. Nobody's saying you have to go all the way down the rabbit hole. So don't frustrate yourself. Make sure you're having fun. Make sure you're getting out there and flying. If messing with this stuff and tweaking things and really, getting into the nitty gritty is fun for you, I mean, it's fun for me. That's why I do this. If it wouldn't be, I just wouldn't do it. I would do other things. So I like getting into the nitty gritty. I'm an engineer, so I mean it's kind of like inherent in how I am, I guess. I don't know, but yeah. At the end of the day, have fun. All right, guys. Well, thanks, and I hope this helps. I will also make this PowerPoint presentation at the same link where you can go down below to download the calc spreadsheet and any of the other little stuff I'm working on. I'll just dump them all in that same directory so you can download any of this stuff for yourself. We'll see you on the next one.
Accelerate ideas.